Welcome everyone. Today we're going to be solving this problem here. Show that for a spherically symmetric mass distribution of radius r, the gravitational field outside the sphere, r greater than r, obeys Newton's law of gravitation, and then also show the inside of the sphere for r less than r that the gravitational field has a linear dependence on the distance from the center. And I'm also going to be deriving Gauss's law for gravitational fields to solve this problem. So the first thing we need to establish is let rho of r be the mass density of spherically symmetric mass. And one more thing we know is that for the volume of a little piece of a sphere, so the shell mass, or whatever, shell volume of a sphere, is just going to be the surface area, so 4 pi, and we'll call this radius s, so 4 pi s squared. And then if we want the differential volume, dv is equal to 4 pi s squared ds. So now we know that m of r, which is the mass, is equal to the rho of r, or I guess it'll be of s this time. Yeah. Times the dv is equal to rho of s 4 pi s squared ds. And then if we need to integrate from 0 to the radius, so the integral from 0 to r of 4 pi s squared rho of s ds. Okay, so that's our mass equation. Next, we know that, so now we need to derive Gauss's law for gravitational fields, so we know that the flux G dot dA, this is the flux of the gravitational field, and we know that for a sphere, the G dot dA is parallel, because you always have the area vector shooting straight out, and then G is always going straight in. So they're parallel, which means that G dot dA is just G of r dA. So this becomes the integral G of r dA which G is constant, so we can have G of r integral dA, and then which this is just G of RA, right? G of RA, the surface area is 4 pi r squared, so we have G of r 4 pi r squared. So that is the flux for the gravitational field. Okay. And also, since this would technically have a cosine here, cosine theta, because of the dot product, since they go in opposite directions, there's a negative sign out here. Okay, so now that we have that, and we also know that since G of r is equal to G mass enclosed over r squared, we can set this equal to that, these equal to each other, so we get negative 4 pi GM enclosed. So that's all we need to solve this problem. Okay, so now for r greater than r, we know that m of r is just all the enclosed mass. So we can literally just solve for g of r in this equation up here. So we get negative g of r 4 pi r squared is equal to, there's a negative sign here, right? Yeah. 4 pi gm. So these cancel out, the negative sign cancels out, and you get g of r is equal to gm over r squared. Negative gm in the r hat direction. So this is our solution for the outside of the sphere, which is pretty obvious because this is Newton's law of gravitation, so pretty easy. And then for r less than r, we now need to evaluate this integral because this is going to be the enclosed mass, which is equal to 0 to r, or what did I put? 4 pi s squared rho of s ds. And the issue here is that we don't know what rho of s is, but we're just going to make it rho of s is equal to rho naught. Just make it constant, uniform mass distribution. So this becomes 4 pi rho naught integral from 0 to r of s squared ds, which is equal to 4/3 rho naught r cubed. Pi r cubed. And if you notice, you'll see that this matches the mass enclosed is equal to, I'm just going to call it m of r. M of r is equal to the volume times the mass density. So v rho naught, which is pretty cool. So now we can set it up in our equation. We got up here that the gravitational field is equal to negative g, now it's m of r, all over r squared, r hat. And if we expand, we get negative g times 4/3 pi rho naught r cubed all over r squared, r hat. Then obviously this 3 and this cancels out, and then you get that g is equal to negative 4/3 g pi rho naught r in the r hat direction. And the cool thing to notice here is that we actually have simple harmonic motion. This is a homework assignment I have later this week. I have to derive this. And you see here that this right here is k, and this is x. So g is equal to negative kx, which is pretty cool. Yeah, that's all. So what are our solutions? For outside the sphere, we have g of r is equal to negative gm over r squared in the r hat direction. And then this is for r greater than r. And then we have g of r is equal to negative 4/3 g pi rho naught r in the r hat direction for r less than r, and constant mass distribution rho of r is equal to rho naught So those are our solutions for this problem. Thank you for watching.